All right, let's get into it. How do we build something solid, something reliable, on top of the internet, which is, well, a total mess? We're going to go deep, down to the transport layer, and see how we create this amazing illusion of a perfect, stable connection when really, underneath, it's chaos.
And this is the fundamental problem, right? The Internet Protocol, IP, is what they call best effort. It's like a lazy postal worker who just shoves packets out the door. It doesn't care if they get lost, show up in the wrong order, or if you get two of the same thing. It just routes. So for us to build the apps we all use, we need a hero. And that hero is TCP.
So, how does TCP clean up the mess that IP leaves behind? Well, it's not magic, but it's pretty close. It's really just a super clever toolkit of different tricks all working together. Let's break down the three big ones. Okay, first up, how do you deal with packets arriving all jumbled up or getting the same one twice? Simple. TCP slaps a sequence number on everything. Just think of it like numbering the boxes when you move house. If box 3 shows up before box 2, you know you just have to wait and reorder them. If you get 2 boxes labeled 5, you just toss the extra one. It's so simple, but man, is it effective.
But what happens if a packet just vanishes? Like the post office completely loses your letter? Well, TCP's got a plan for that too. It uses acknowledgments, or ACKs. The receiver has to send a little message back for everything it gets, saying, "Yep, got it." And if the sender doesn't hear that got it message within a certain amount of time, it just assumes the packet is lost and sends it again. Simple as that. Nothing gets left behind.
And finally, how do you know the data didn't get messed up on the way? You know, a bit gets flipped here or there because of a bad cable or something. For this, TCP uses a checksum. It's basically a quick math problem that the sender does on the data. It sends the answer along with the data. The receiver does the exact same math problem. If the answers don't match, boom, the data's corrupt. It gets thrown out.
But, all of this incredible reliability and careful management, it isn't free. There's a price to pay. The source material calls it the connection tax, and I love that name, because before you can send even a single byte of your actual app's data, you gotta pay this tax.
And you pay this tax with something called the three-way handshake. It's this formal little dance to make sure both the sender and receiver are ready to talk and are synced up. It goes like this. First, the sender says SYN, which is like saying, "Hey, want to talk? My starting number is X." Then the receiver says SYN/ACK, which means, "Sure, I see your X, and my starting number is Y." Finally, the sender says ACK, "Cool, I got your Y." Only then, after all that back and forth, can you actually start sending data.
So think about it. During that entire handshake, what's your useful bandwidth? It's zero, a big fat zero. You're literally doing nothing but waiting. And if you have an app that needs to make lots of tiny, quick requests, this waiting time, it adds up. It can absolutely kill your performance.
This is why, as engineers, the #1 rule is don't pay this tax more than you have to. So how do we get around it? Connection pools. It's a brilliant idea. You just open a bunch of these connections ahead of time and keep them open, kind of like cars waiting with the engine running. Then, when your app needs to send something, it just grabs one of these pre-warmed connections and goes. No handshake, no delay. All right, so our connection is up and we're finally sending data? Awesome. But we can't just open the fire hose and blast data as fast as we can. Nope. TCP also has to be a good citizen of the internet, and that means it has to carefully manage the flow so it doesn't drown the receiver or the entire network. And it's super important to understand there are two different things going on here. First, there's flow control. This is all about protecting the receiver. Imagine you're talking to a friend and they're like, whoa, slow down, I can't write that fast. That's flow control. The receiver is telling the sender how much buffer space it has. But then there's congestion control. This is about protecting the network itself. This is more like those traffic lights on the highway on-ramp, They're trying to prevent a total gridlock by controlling how many cars get on the road.
This brings us to a fundamental, mind-blowing law of the internet. Your maximum speed, your bandwidth, it isn't just about what you pay your ISP for. It's always a function of your window size divided by your round-trip time, your latency. Think about that. No matter how huge your internet pipe is, you are always limited by the speed of light and the distance to the server. And that right there is exactly why we go to such great lengths to put servers as physically close to users as possible.
But what if you don't need all this hand-holding? What if all you care about is raw, unadulterated speed? Well, for that, my friends, there is an alternative, and its name is UDP, the User Datagram Protocol. Just imagine a fast-paced online game, right? A packet gets sent with a player's new location. Now, what if that packet gets lost? The last thing you want is for TCP to stop the whole game, ask for that old packet again, and then deliver it a second later. By then, it's ancient history. The player has already moved again. In this case, you'd much rather just drop that old packet and get the newest, freshest data.
And this really sums it all up perfectly. TCP is kind of like the responsible parent. It's reliable, it's orderly, it's very careful. UDP? UDP is the rebellious teenager. It's fast, it makes zero promises, and it's totally fire and forget. If you choose UDP and you still need some reliability, well, that's on you. You've got to build it yourself in your own application code.
So let's zoom out. What's the big takeaway? We've talked about sequence numbers, handshakes, buffers, all this complex stuff. Why should you, as a developer, actually care about any of this? Because honestly, here's the deal. Understanding what's happening underneath your code is what separates the pros from the amateurs. When your app is slow, when things are getting weird, knowing about that handshake tax or how congestion control works, that's what lets you actually diagnose the real problem instead of just guessing. It's a huge marker of a senior engineer. And all this leaves us with a really fascinating question about the future, right? Because modern protocols like HTTP3, they're actually being built on top of UDP. They're trying to get rid of some of TCP's old baggage. So, does that mean the era of built-in, one-size-fits-all reliability is ending? Are we moving into a world where every developer has to be a bit of a network engineer, building their own reliability from scratch for every single app? It really feels like the very foundation of the internet is starting to shift.